Welcome to the session. Greeting of the day. In today's class, we are going to start about a new unit. It's nothing but a thermography. We are in the entire module of non-destructive testings, and we have seen few processes. Out of importantly, there are 8 topics are there. We have seen some 8 topics. Non-destructive testings. Importantly, we have seen these 8 topics. In these 8 topics, we have already covered a few methodologies of visual testings, liquid printed testings, matic particles, eddy current, radiographic testings, ultrasonic, acoustic, and at last now we are going to talk about in this the coming unit of infrared thermography. The last one very important. Here we are going to measure with respect to change in the temperatures. So this all belongs to non-destructive testing techniques. Out of this, we have already covered this each methods of visual, liquid, matic particles, eddy currents, radiographies, everything. So at last, the last one of infrared thermography. See, it is also one kind of non-destructive testings only. As I told you earlier, according to visual inspection is a non-destructive. It means we are not going to disturb the sample. It means we are not going to break the sample. As just we are going to pass something, maybe the X-rays or maybe the gamma rays or maybe the ultrasonic or maybe the matic particle, matic field, any one other methods we are using to detect the defect which are discontinuity inside the specimen. So in the same pattern, we are going to see about the previous one. Here we have considered a lot of information with respect to various methodology to define the discontinuities. Here we are going to use the temperature as one of the method. That is nothing but an infrared thermography. So it is one kind of a non-destructive testing. Here just going to detect the problems, maybe the problems or defects or discontinuities, whatever that mean, that occurring into the material, maybe the surface or maybe the subsurface, because we are going to find the temperature formation where the highest temperature is received. We have seen some of the images in the films or something movies or in the advertisements like that animated one. Somewhere it will be on red color, somewhere it will be the yellow color, somewhere it will be the green or blue color. That simulation gives us a result. So that we are going to generate here with respect to direct implementation of the infrared camera over the specimen. It is going to give us that camera is going to give us a multicolored temperature distributions over the specimen. With respect to that, what is the temperature differences are there on each point of the work material we are going to find. So that is how we can understand the stress. High stress is there, a low stress is there, high temperature is there. It is a high concentration of temperature point. If high temperature is induced there, definitely there will be a problem or otherwise a defect causing, because a high temperature obviously creates some martensit formations or loss of properties or the crack initiations, breakages or matic properties, erasing of the matic properties. Heat is always a problem, or solidification problems or solidification crackings. Somewhere all this will happen. Sometimes it will be useful like the Curie temperatures, all these available. But even though the differences we need, where it is good, where it is bad, that we have to identify. Then we need temperature. This point is this point is this. Red color is the highest temperature, green color is the lowest temperature. So likewise we can able to identify. You see here, we are going to detect problems or defects occurring in the material during the manufacturing process through, I have some 3 points here, through some images. The digital camera is going to take the photo as like a normal camera, but it is an infrared camera which while during the live video shootings it shows the temperature difference. Then we can digitally we can record those things through the images. It means through the images we are through some temperature accumulations where the accumulation of red colors or through some temperature differences. One of temperature accumulated is 900 degrees centigrade. One temperature accumulation is around 650 degrees centigrade. So that high temperature will maybe considered as a red color, and the other temperatures can be in the lower blue, green, such yellow, or other ways we can something we can use. See here in this picture, what I have shown you already, that is what here I have represented in a simulated way. See, in the flight which is having a progressive flight is going in some directions. This some directions what happens giving you some stress factors, some image factors. It means the front face which is going to penetrate in forward direction getting some red color, and also the wings which are already directly in contact with the air which is penetrating over, which helps to move, are also in red color. The other parts which carries the load of the passengers and other things are around other various colors like a green and dark blues. So this all represents have some temperature. It also have some temperature indications that we are going to capture the method of thermal cameras, and some other active method, passive methods are there that we are going to see in our these units in upcoming few lectures. So thermography and non-destructive testing is also known as some game names I am giving are thermal inspections, a thermography, that is what I have given here also a general name, a thermography as a heading, and thermal imaging because we are using cameras, thermal imaging, thermal wave imaging, thermal infrared thermal testings all belongs to a similar pattern. We are using a heat. Heat is the main concern here. It was first developed. It was first developed for military purposes in the late 1950s, 50 years before, and 1960s by Texas Instruments, Hughes Aircraft, and Honeywell. It involves the measurement or mapping of the surface temperatures. Mapping is nothing but a classification, so where in this spot, this spot, this spot we are going to identify, that is called as mapping. So that a mapping of the surface temperatures as the heat flow to and from somewhere, or otherwise through the specimens, through the aircraft, through the railway tracks of an object. So this is how we identify to, from, through an object. The simplest thermal measurements involve making a point measurement with a thermocouple. We know this method of generally we are using thermocouple measurements. It is a temperature measurement device, and also we are this thermography. Somehow with the advanced methods of cameras and all we are using now. The advantages of this thermographic inspection. The non-destructive testing methods. The non-destructive testing methods is useful in locating a hot spots. It means a hot temperature spots. We are traveling in somehow we are giving a boiler plant in the fabrication process, and we want to know where the hot temperature is involved, how much it is involved, how much it is the protective layer, how much it is the maximum temperature withstanding ability. For that cases, even though we measure through some other methods, hot water temperature measurement, all these sensors are available, but even though this that all works are active methods, passive method that we are going to cover here with example. See where the heat is generated, where that we want to measure. For example, I have given a bearing that is wearing out and starting to heat up, increasing the friction. This friction causes heat. Yes. Here, understanding that we are doing some in-service monitoring also, not only the fabrication. Fabrication, we have created the bearing, but at the same time it is going to wear out in in-service conditions, where in the plant where it is installed and then it started to work. That is in service. During the time the friction created, during the time heat is generated. During the time we want to, our product which what we delivered, the bearing to sustain the temperature. So what we have to do? We have to do trial and error at our fabrication site itself. How far it will wear, how far friction it can able to withstand. How we know these things? We should measure, we should inspect. Then we understand. So for inspecting, we are using some methodology. This methodology is to measure the heat. Those magnetic particles or the radiography particles are used to measure the crack discontinuity what is present here. Here also discontinuity is there, but it is a heat concerns. So that is how. Even though other methodology also here also possible to do the crack possible. Vibrative thermography is there. So we have sent the vibrations and it vibrates and it reflects. Therefore, this thermography component will attract those infrared radiations or vibrations or wavelength, and it absorbs converted into digital form. So we will see this all this in the image here. What are the images kept in the left side? This image. In the image there are so many colors. What I told you in general it is given. Our colors, all the colors having a different meaning. Maybe here this is a red color. Red color is getting a maximum stress or maximum heat, that is generation at the particular point. Yes. How the stress and strain is passing in, acting through the particular materials. So stress strain curve we are generating, or otherwise the maximum temperature, lowest temperature we are calculating by mapping it. It means by simulations, everything, taking the various multitasked videos or pictures, and then we are identifying. And however, see, however, the temperature is moving inside the material as like a heat map. From one point to another point, it changes from one color to the another colors. From particular space shuttle at a landing process. So here this is the example of this one. When an aircraft or space is landing, we want information. What happens there? We are suffering to land a craft or anything some on the lands. In the moon we can't able to land. So there's a problem there. Some temperature differences or some other problems are there. Why we should measure. Some components are required there. So a digital format they are attaching over there and they are sending. It works through thermographic and other heat absorption materials. Not only here. A principle. A principle of thermography is based on the physical phenomenon that any body of a temperature above the absolute zero, that is nothing but 273.15 degrees centigrade, emits electromagnetic radiations. The emitted infrared energy is function of objective temperature. This is what we are going to measure. The object temperature is emitted, and it is nothing but infrared energy that we are going to take out. Two dissimilar materials possessing different thermomechanical properties would produce two different thermal signatures. It means one in one temperature, another maybe in another temperature according to its thermal capability, thermal ability. That can be revealed by any infrared sensors are called as a thermographic camera. So now we are going to extend our studies towards this of thermographic cameras. Before going there, I want to express something where these infrareds are available. Where this infrared are available here. You see, in the x-axis, I have a various wavelength. It is nothing but we have seen in the while the same image we have seen in a radiographic unit is named as a spectrum, and we have seen how far the gamma rays, how far this X-rays are more dangerous, and it's harmful to life threat factor. So the same spectrum I have taken again here. We want to find where this infrared falls over the spectrum. In x-axis I have taken the wavelength in micrometers, and in the y-axis various factors like gamma rays, X-rays, radio waves. So all this its intensity, energy. It is y-axis is the sum of energy, how much it is. See in the x-axis, when it is in the range of 10 to the power of minus 8 micrometer, so the gamma rays are there up to some of the extent, and it is overlapping here over the X-rays up to 10 to the power of minus 5. Let us assume 10 to the power of minus 8 to 10 to the power of minus 5 is in the gamma rays. Beyond the 10 to the power of minus 8, it is nothing but some other very dangerous cosmic rays are there. And then from 10 to the power of minus 5 towards the 10 to the power of minus 2 and later to nearing to the 1, it is X-rays. We are here. this X-rays. And later we have some ultraviolets, we have some visible ranges nearer to the 1, and later from 1 to 10 to the power of 2, it's nothing but wavelength is increasing. We have seen wavelength is nothing but a gap between a frequency. Some images also we learned how many frequencies passing per second, wavelength per second. It is called as frequency per second. It is called as wavelength. So here 10 to the power of minus 8 frequencies per second will form there. So the micrometers wavelength. See how much wavelengths are there. Here infrared is a very general. Infrared is about 10 to the power of 2 micrometers over there after that. So here this is what our thermal radiations also in those visible ranges, in this of ultraviolet ranges, in those of infrared ranges. This is our study now, infrared thermography. So visible ranges okay, and over there not visible ranges we have to use some cameras to find that temperatures how far it is. So that infrared we are using to find the thermal radiations. Here it is given the thermal radiations. So this is our unit of study here. And then about 10 to the power of 2 micrometers we have a radio waves. The visible range is here already over. Very less ranges. Over there we have infrared. Over there we have a radio waves. Now this is our hot topic of study. See what I have talked earlier a little bit. I have concluded as a small gathering informations. A cosmic rays beyond 10 to the power of minus 8 micrometer. Yes, and gamma rays from 10 to the power of minus 8 to 10 to the power of minus 5 micrometers. This ranges from here to here. And X-rays around 10 to the power of minus 1 after the gamma rays. After the gamma rays around 10 to the power of minus 1 here, this point. So from here to here, from here to here. And then later we have ultrasonic rays and visible rays and infrared from 1 to 10 to the power of 2 here, this ranges. And lastly we have the radio waves with a long range of 10 to the power 2 and above, 10 to the power of 2 and above. So that's how we understand where we are going to work now. Our working zone is infrared is here from 1 to 10 to the power of 2 micrometers of wavelength. We are entering into thermographic cameras. So types we have to see. So this is our study we understand now. So it is also known as infrared camera, or otherwise it is also known as infrared thermal imaging camera. Some different names we are using. It's a device that forms a heat zone image, that's a red, blue, green or multicolored images using infrared radiations similar to a common camera that forms an image using a visible light. Yes, instead of visible ranges of 400 to 700 nanometers range of a visible light, the infrared camera operate in the wavelength as long as 13,000 nanometers. So the same what is converted, acting after the visible limit. So after visible limit it is somehow the next range after 1. So it is around 10 to the power of 2 micrometers, 12,000 nanometers or 13,000 nanometers. See, the focus lens of infrared camera are not made of glass like as usual, like normal camera. It is not made of glass. A glass, because you see because a glass blocks a long way of infrared. The normal glass are not capable to pass through this infrared rays. Therefore, it is blocking. Therefore, we cannot use. We won't get the information. We need to get the information. Therefore, we are not using that glass. So, a special material such as germanium or sapphire crystals are used for these particular purposes. What is the particular purpose? Infrared camera glasses, which is used to pass through this wavelength of infrared light sources. Germanium lenses are also quite fragile, so often have a hard coating to protect against the accidental contact. It is also brittle somehow. Therefore, we are using some hard coatings over there to protect from the accidental falling down to escape from the damages. That is also one of the reason. The germanium itself, it is wanted to permit the rays, and also it is having a hard coating which increases the price of the camera. Normal camera is somehow we can purchase 30-50 thousands a digital, very well digital cameras, but these infrared cameras are costlier than that because it is going to work out on a longer temperatures. It means our aim is to measure the working condition, not at the closed or not at the room temperature specimens. We want to find the temperature differences, what happening there through non-destructive mode. So measuring the temperature through conductive, this thermocouple, all touch methods are different. But here, due non-contact method, use only the camera, and we are seeing through the camera. It is going to give you some informations. For that purposes, the camera is going to be in contact with that warm room. We ourselves wanted to go there. It is warm room. On that warm room, camera is a plastic and surrounded by some covers. It also become damaged when the high temperature environment is there. Therefore, we want to protect those camera and protect those lenses, and we should permit those infrared light sources to the digital systems, and then only we will receive some informations like red, blue, green colors, which gives you different temperature indications as described programmed. Therefore, we are using germanium, that glasses and hard coatings, which makes a costlier of this camera. So that's what I have written here. The highest cost of this special lenses is one of the reasons why thermographic cameras are also so called costly in the market. There are several types of thermographic camera. Our study is here, starts from here, are available. I am dividing into two types. We have to see every type having some subdividing types also. So number one is cooled infrared detectors, and number two is uncooled infrared detectors. It means you see, the cooled infrared detectors usually will be helpful for high temperature applications because the name itself says it is cooled. We are supplying a coolant or any cooling systems to cover or protect the camera. In such a way, camera can go nearer to the very hot zones. So that is called as cooled infrared detectors. Uncooled infrared detectors may be at a normal temperatures, maybe the ambient temperatures or normally working conditions. We can able to observe that is very cheaper also. Uncooled infrared detectors. We see one by one. It is also having types. Now, number one I have taken as a cooled infrared detectors. They are typically contained in a vacuum sealed case and also a cryogenically cooled. It is some kind of a liquid nitrogen which makes the setup a cooling when it is on that. We have here that word cryogenic, a cool minus 196 degrees centigrades. So that and all some creation, not minus 126 specifically. Somehow they will make some adjustments to keep the cameras in a chilled conditions, which will be helpful to go nearer to the hot spots to take the measurements. The cooling is necessary for operations of the semiconductor material used in the camera. Somehow the semiconductor or any other all parts, various parts. On thermal imaging, camera is going to be heated definitely. Yes, when it is in service, when it is going nearer to the component. So it loses its property and become maybe out of order or failure or damage, which is that 50,000 of money will be wasted. So what we have to do? We have to protect through some covers. That is why we are using some cryogenic cooling systems or maybe some cover items that we have to. Next point I have given to see. So to work into that high temperature, adding some cooling jackets as a cover which lowers down its temperature and make the camera as stable to work over there. A typical operation temperatures ranges from 4 Kelvin to just below the room temperature. In the room temperature, somehow we are coming down. There we can use uncooled infrared detectors. Here we are using above that. That is what it is. A cooled infrared detectors are in need. Now the next one, uncooled infrared detectors. The uncooled thermal camera uses a sensor stabilized at a temperature close to the ambient using a small temperature control elements. Here it is already uncooled. It means temperature also lower. Therefore, we can use some sensors to detect very nearer to the ambient conditions, and very small temperature control devices or any small cooling systems can be used if required. A modern uncooled detectors uses sensors that works by we have seen some resistance changes, voltage current changes by magnetic property field changes. When the material is heated, magnetic properties also will change. Up to certain limit, we can able to use that method to identify what it is, how much temperature is increasing or decreasing. So that is what the resistance are all converting into some electrical formats. So change in the resistance, change in the voltage, change in the current when heated by some infrared radiations. You see some important point here. Uncooled infrared have lower sensitivity than that of the cooled infrared detector, because cooled infrared detector approximately perfect calibrated stabilized one. Even here we are not using some cooling systems. If the camera is lightly heated, subjected to infrared radiations, it may give you wrong results, wrong radiation. That is why uncooled are not much more sensitivity or much more precious than the top cooled one. It means cooled is more precious, uncooled are less in precious readings. This is how our study, it means we are in position to understand these types. Okay? The types of thermographic inspection. The infrared thermography, I am starting here and dividing into two categories. One is the active mode. You want to see all this one. One is active mode, passive mode, and one more. That is again I am dividing into a mechanical internal excitation or optical external excitation. Internal, external, active, passive. And further, the internal excitation I am dividing into vibrothermography. To detect, this is what I told you, which is used to find the crack which is inside the specimen subsurfaces. And vibrothermography again I am dividing into another two methods of burst mode and lock-in mode. External excitations I am dividing again into this lock-in thermography or pulsed thermography. Each one having some different types of concepts. So this is all one by one we have to see. In today's class, we have given some introduction of regarding the thermography, about this thermal radiography and spectrums, what we have seen, and what is the principles, how it is working, and we have divided this infrared thermography into some various subcategories of active methods, passive methods, and vibrothermographies, burst mode, lock-in modes. Some we have given some classifications. So these classifications we have to go through one by one. We will see. The remaining part of the subjects, we'll see you in the next session. Thank you.